Alright, well, so in class we're going to look at one more example from section 8.2. This is another application. Still the street intersections, but this time there's only 3. Okay, so we have I2, or I1, I2, I3. So again, we're going to do ins equals outs. Alright, we're going to start with the first intersection. So at this intersection, the ends, things that are pointing into the circle, is this road, which is 13, and actually x, because this is a one-way road going this way. So x plus 13 are the ends, and then that's equal to the outs pointing out of that intersection because of the way the roads are oriented, is this 15 right here, and then whatever y is. So y plus 15. Alright, and now let's go to the next intersection, this one right here. And the ends are 13 coming in this way. Alright, and then this is a one-way road coming diagonally this way, so z. So the ends are 13 and z, or z plus 13. And then coming out of that intersection, again, because of the one-way road, we got an x coming out of there, and then the 8 up here coming out. So x plus 8. Alright, and then we'll move to the third one down here, 3. Alright, so the ends, the arrows pointing into that intersection are 5 and y. So y plus 5 are the ends. And then what's coming out of that intersection is this 8 right here, and then the z. So z plus 8. Alright, so there is our system. Now, the problem with this one is different from the last one. The last one, if you notice, if you remember, we always had the variables were together and the numbers were together. But now we have variables and numbers on each side. We always want to put variables on one side, constants on the other. So I'm going to move the y over to join the x by subtracting it, and then the 13 over to join the 15. So my I1 equation will actually end up being x minus y. Alright, if I subtract y from both sides. And then 15 minus 13 is 2. Okay, so this equation became x minus y equals 2. I'm going to change it back to red so you know which equation is which. Okay, for I2, that's the blue equation. I'm going to move the x over here with z, the 13 over here with the 8. So that'll be a minus x. I'm going to move it over, plus z equals, then the 8, I'll subtract the 13 over. So I'll end up with 8 minus 13 is negative 5. Alright, and then again, the bottom one, switch to black. I'm going to move the z over with the y, so that'll be a positive y and a minus z. Alright, and then that's going to equal, if I move the 5 over to join the 8, I'll get a 3. Okay, so there's my system of equations. Now I'm going to set up a matrix for this. Alright, once again, this is there's 3 variables, x, y, and z. So there's 3 variables and a 4th constant. So 3 equations, 4 variables and constants combined. So this is a 3 by 4 matrix. Then I'm just going to put in 1s for the x and negative 1 for the y. And then there's no z in this top equation, so 0, and then a 2. Alright, and then a negative 1 for x. There's no y in this one. 1 for z, and negative 5. Alright, and then there is no x's again. 1 y, and negative 1 for z. And that's equal to 3. So there's my system of equations. I'm going to back out. Come back in, RREF, matrix B, and I get this. Again, it's a dependent system like most of these are these car problems, these intersections are going to be. So there's my matrix. I'm going to stick it in here so we can solve it. Alright, so there's what we end up with. Now this is x, z, and so that's a x minus z equals 5. Remember, I'm going to solve it for x. I'm going to solve the ones that have the x and the y. I'm going to solve those in terms of those variables. So I'm going to add z over. So I end up with x equals z plus 5. Alright, this is y minus z equals 3. Alright, so again, adding z over, I get y equals z plus 3. So the form of these solutions are going to be x, y, z, like we talked about before, but this is x, z plus 5. This is y, z plus 3. Alright, and then z gets to be free. Okay? Z can be, has to be positive, right? Because we have z is a number of cars on a road, so z has to be positive. But because there is no subtraction in any of these, we're not subtracting z from anything. We don't have that upper limit like we did on the last one for z. Okay, now there would be some sort of finite upper limit that this road can handle, okay, but it doesn't tell us that information in the problem. And there is no understood upper limit from z because of subtraction in this thing. So anyway, this is what this ends up looking like. And then if you were told, if the problem says, what if z is 18? Just making up a number. If z is 18, then this is 18. This is 3 more than that, so this would be 21. And this is 5 more than 18, which would be 23. So that would be a particular solution. Okay, and that means that if you have 13 cars coming into this intersection right here, that's an n, and then this n is x, which was 23. Alright, that's 23 plus 13 is 36. Well, 15 are leaving, so 36 minus 15 is 15 right here is 21, and that's what's leaving on Y Street right here. Okay, so this would mean all of these intersections have to have the same amount of cars coming in as going out, and it's a dependent system. It all depends on, these are the cars that are coming in, but it all depends on how they're turning. If this car that's coming in here turns to the left, then it's adding to x. If it stays straight, then it's part of this 8 cars that are leaving. So that's why it's a dependent system, because inside here, this triangle, x, y, z, cars can change, and as they do turn, as they change the roads that they're traveling on, we get that dependency. X and y depend on what happens with z here, what that car does. Y and z depends on what happens with x here. Okay, but the flow rates coming in and out of these intersections, along with that in the middle, creates your system, and then you're going to get dependency with these. So remember, when you get dependency, REF your matrix, get it down as far as you can, and then solve those other 2 equations for x and y, and that's how you'll write your answer, your final answer.